Right, so here we have another three-wire circuit problem to try to solve. And this time we have to deal with line resistance, or resistance, internal resistance within the conductor and voltage drop. And we need to apply that to our three-wire circuit. So for this question, we're going to have to try to figure out what the voltage is on line 1, 2, or sorry, on load 1, load 2, load 3, and load 4. All right, so this is a bit of a process, and we can't just, at this point now, we can't assume that we have 120 volts at each of these loads, even though that would be ideal. That's not going to happen because we do have a slight voltage drop across the conductors at this point, because there is always a little bit of resistance in those conductors. So, what we're gonna do, the first thing we gotta do here is we are going to assume a direction for the current going through our loads. So I like to always go clockwise, but we're gonna assume that our current here is flowing this way through our source, this way, and this way here. So it's going this way through all our loads clockwise, and then back through line 2. So we assume that clockwise direction for our currents. You could go the other way too, that's totally fine as long as you're consistent. All right. So now that we have our direction, we can start to figure out what current is actually flowing through our conductors. So if we start toward the right side of the equation here, of this drawing, we got 7 amps going through this load. So it's obvious this conductor is in series that this has to have 7 amps going through it as well. Again, in that clockwise direction. Same with here, we got 4 amps going through this conductor because this 4 amps is carried through in series. It just shares one single conductor. Current has to be the same. Now, if we follow along, our 4 amps is flowing this way. Our 9 amps is flowing in this direction. They're going to converge at this point here, a junction, and be added together to flow down this section of our circuit. So 9 plus 4 is 13 amps flows at this point here. Likewise, if we have 3 amps flowing down load 1 and load 2 is drawing 7 amps, then we must at this point here have the combination of both those currents, so 10 amps. Again, flowing in that direction. All right. So now we got to figure out what's flowing down our neutral. We know that the neutral just carries the unbalanced portion of the load. All right, the imbalance between line 1 up here and line 2. That's the neutral's job. So if we got 7 amps up here, and we got 4 amps down here, then the imbalance of that, or the difference, is going to be 3 amps. And now we got to assume a direction as well. So our 7 amps is flowing this way into the load. 4 amps is flowing back to the source. So we need to have that 7 amps going into the load match what's going back into the source. What comes in must come out. So this 3 amps then has to be flowing back into the source. So we've got 3 amps and 4 amps for a total of 7 amps going back in. Okay, so we figured out our current inner neutral at that section here. Now our neutral continues on, and and is in between load 1 and load 3 as well. Well, all we're going to look at here is the current in line 1, current in line 2, and the difference between the two. So in this case here, we got 3 amps. Is the difference between 13 and 10. We got 10 amps flowing into the load, and now 13 flowing back into the source. So in this case, the 3 amps is actually flowing into the load. So now we got 10 plus 3, 13 going into the load, 13 going back to the source. Those match. That's perfect. Okay. So let me get rid of some of this clutter. Alright, so now that we have our resistance and our current at each of our conductors, each of our wires, we can now put in our voltage. We'll make that a different color. So our voltage drop then, at this point here, is going to be 1 multiplied by 10 amps, give us 10 volt drop at that conductor. 7 amps times 1 is going to be 7 volts. They've made it easy for us by making the resistance 1, obviously. So 1 ohm times 4 is 4 volt drop. In that conductor, 3 volt drop. In this conductor, 13 volt drop. In that conductor, and a 3 volt drop in that portion of the neutral. Okay, now that we have our voltage drops in all the conductors, we can now figure out what our voltage drop is going to be in each particular load. So let me change colors once again. Now what we got to do is we solve each of these rectangles, we call them loops, individually. So we're going to draw in a direction of our loop. So our current in this loop is going to leave line 1, just like it does up here. So that our direction is dictated by the direction that we've set from the beginning. It's going to flow this way and then back to the 120 volts there. So our direction in our loop is going to be this way. Right? And that's really important to do. And what that's going to tell us is whether our particular voltage in the neutral is going to be a rise or it's going to be a drop. So Kirchhoff's voltage law states that the voltage at the source needs to equal all the drops and rises throughout the circuit. So if we have a 120 volt rise or 120 volt source, we drop 10 volts in this conductor here. So now we're down to 120 volts left for the load. However, our current going through this loop is actually opposing the current in the overall circuit. It's flowing this way here. So this 3 volts is not considered a drop, it's actually considered a rise. So we've lost 10 volts up here, but we gained 3 volts in the neutral, and so now we are at 113 volts for that particular, for load 1. All right. If the neutral ends up being a rise on one side of the 3-wire circuit, it's going to be a drop on the other side, and we'll see that right here. So we've solved loop 1. Now we're going to do the loop below it, and you got to do this from left to right, or from the loops closest to the source to the loops furthest away from the source. So our loop direction is always going to remain the same, dictated here by the direction in line 2, in line 1. So it's going clockwise. This time we start with 120 volts, that's our source. And this 3 volts now, it becomes a drop as well because our loop direction, our current through this particular loop, is the same direction as the loop going through the as the current direction going through the neutral. So we get a 3 volt drop. So now we're down to 117 volts, and we also drop 13 volts. So we have 104 volt drop at the load. So now our 104 plus 3 gives us 107 plus 13 equals 120. So Kirchhoff is satisfied. All right, let's do the next loop. So now we're working our way from left to right. We're going to solve this loop here. So we're going to set the direction. And this time, instead of using the 120 volt source, we're going to use the 113 volts left over at that load. And that makes sense because as we get further and further away from the source, we're going to be losing more and more voltage in our conductors because of the shear length of the conductor. So we're not starting with the 120 volts now, we're starting with the 113 volts here. All right, let's change color again, hopefully for clarity's sake. So we're starting with 113 volts this time. We set our loop direction, and we have 113. We're going to subtract 7 from that, so that's going to be 106. And then through this loop, the current going through load 2 is actually matching the direction of current flow through our neutral. And so we're going to get a drop of 7 and a drop of 3 for a total drop of 10 volts, giving us 103 volts at load 2. Now, clearly this isn't like a realistic circuit. As the code book says, you're only allowed a 3% total drop in any of your branch circuits, so you would only ever be able to have 3% of 120, which ends up being I think 116, slightly over 116 volts. So obviously 103 volts is not going to be adequate, but this isn't necessarily a realistic circuit. All right, finally the last loop, we're starting with 104. We draw in our loop direction. This time our current through the loop is opposing the current through the neutral, and so we actually gain 3 volts. So we're up to 107 volts, and then we lose 4 volts. So we are back down to 106 volts left over for load 4. And that completes the question. So we got load 1, 113 volts, load 2, 103 volts, load 3, 104 volts, and load 4. Oh, we must have done something wrong here. So let's see what that was. So it's definitely always good to go back and check your work. But here, load 3, we had 104 volts. We gained 3 volts, and then we lost 4. So we are at also 103 volts here. And that concludes that question.